I did my little rant about how the law of conservation of energy should be said with echoes and drama. It's a very, very fundamental law of the universe, which brings us to a question, Aiden. What is it? So here's what it says. Energy is neither created nor destroyed. It can only be transformed from one type to another. What this means is if you're looking at a closed system, and what do I mean by a closed system? That will be a system with no outside sources of energy. You're not plugging something into a power outlet. You're not adding extra gasoline to the motor. If you have a closed system, the total amount of energy at the start and the total amount of energy at the end must be the same. That is hugely profound. That explains why a large number of objects in the universe behave the way they do. For example, it says this: both the kinetic energy and the potential energy of a block sliding down a ramp are shown below at the bottom. So here's the bottom. Ben, this is so easy, you can do it in your head. At the bottom, what's the total energy that this system possesses? What's 0 plus 75 in your head, please? The law of conservation of energy says that anywhere there's going to be 75 joules of energy. So let's go trundling up to here. How much kinetic energy do I have as a number right here? So how much must I have as potential energy? Yes. Okay. Now, potential energy in this case is due to height. It's mgh. As it falls or slides down the hill, it loses potential energy. Okay, then Ben, how much kinetic energy must it have right here? And what that means is it went from 0 to 25. Kinetic energy, Maddie, is the energy of motion. This is why it's speeding up. It's gaining kinetic energy. The energy's got to go somewhere. If it's losing potential energy, that energy cannot vanish. It has to go somewhere. Tori, how much potential energy do I have right here? Even less, I have more kinetic energy. That means it's going faster. And in fact, when is it going its fastest? Right at the bottom of the hill. So among other things, this explains why objects will tend to speed up as they lose energy, as they go down a hill, as they lose potential energy. Sorry, just forgot to give the tape. Can you put it face down on the appropriate block? And your timing is perfect. We just started the next unit, next lesson. I'm probably going to abbreviate the law of conservation of energy as C of E. Here's what it says in English. Okay, need your focus here, guys. Can't have a big distraction. The amount of energy in a closed system never changes. Of course, I'm not going to write out the English version. As an equation, it says this: stored energy initial plus motion energy initial, what you start with, equals stored energy final plus motion energy final, what you finish with. But of course, I'm not going to write that out either, Owen. I'm going to abbreviate. What was our abbreviate for stored energy? 2 letters. PE, potential energy. So as an equation, it says this: PE initial plus, what was our abbreviate for motion energy? Also 2 letters. KE, kinetic energy, equals PE final plus KE final. Check your formula sheet. Did I give you that? Yes. Did I go PE plus KE or did I go KE plus PE? Doesn't matter as long as it's initial plus initial equals final plus final. And that's how I've always memorized it. We can even be more accurate. Now, this works if we're ignoring heat and if we're ignoring friction, but now we can be a bit more accurate. Often this year I've pretended friction doesn't exist. If we want to include friction, we can say this: kinetic energy initial plus potential energy initial, or potential initial plus kinetic initial plus initial equals, Emily, final plus final plus heat. If the numbers don't balance up, you've lost some energy to heat. Carson, a great example of the law of conservation of energy is skate parks, half pipes. So here is a half pipe. Right now, I'm going to turn friction to 0. And I'm going to lift this skater up. When I lift this skater up, what kind of energy am I giving them if I'm increasing their height? Gravitational potential. So watch, you should see two of the bars increase. The gold one is the total energy. The blue one is the potential energy. When I let this skater go, what's going to happen? What's the potential energy going to turn into? The energy of motion. There you go. Is the total energy, is it changing, Hannah? What's changing? At the top, I come to a stop for a split second. All potential. That's why you come to a stop at the top. You've given all your kinetic energy to potential. What about at the bottom? What will the potential energy be exactly as a number? So what will all the energy have turned into? Where will I be going the fastest? Why? It's all kinetic, baby. No potential. Now, this is what the world would be like if we had no friction. In real life, what you need to do if you're skating is you need to add energy from your body. That's why you shift your weight and press your leg. You do force times distance. Here, I'm just going to turn friction on for a split second. Is the total energy changing at all? The gold bar, is that changing? The gold line, the yellow line, is that changing? That's the law of conservation of energy. What line do you see slowly getting bigger? The red. We're losing energy to heat. The total energy, though, is staying the same, but we got less energy left over for kinetic and potential. This is a better illustration of how it works. Typically, if you have something that's moving back and forth, it's losing some energy to heat and sound and other dissipative energies. Eventually, you'll come to a stop. What will all of the energy eventually be transformed into? Starts with letter H. That right there is also, spoiler alert, the fate of the universe. The fate of the universe, eventually, all of the heat, all of the energy in the universe will spread out as heat. And you can calculate then how much the temperature of the universe will be. It'll be about 2 degrees Kelvin. Everything will freeze. We are all going to die. You're going to die someday, the end. The heat death of the universe, though, isn't for a few trillion years, so none of you will make it that far. But spoiler alert, that's what's going to happen to the universe. The law of conservation of energy, Show, oh, I have my marble energy transfer device. Sorry for those of you at YouTube, on YouTube. Back here, I've set up my track. When I lift this marble up, what kind of energy am I giving it? Now it's turning into some kinetic. Can you hear it? Some energy is getting bled off as sound. All of that potential turned into kinetic, but also these moved, they bled off some kinetic energy. This moved, it bled off some kinetic energy. This moved, it bled off some kinetic energy. But if I added up all of the sound energy, all of that kinetic energy, that kinetic energy, that kinetic energy, and how much kinetic energy the ball had at the end, it would equal mgh. It would equal mgh. Oh, we'd lose a tiny bit to friction, but we're ignoring that. So I have that out. You can play with it later on after you've done the homework, but not right now. The law of conservation of energy. Bouncing a basketball. Anybody here on the basketball team? No basketball players? So when you're bouncing a ball, at the bottom, it's all kinetic, like the skate park. At the top, it's all potential. So of course, the ball comes to a stop. Tori, put your phone away and leave it away. Or better yet, put it on the counter behind you, please. Oh, I thought you were looking at your phone. I apologize. Ben was staring at it too. I thought you were being distracting. Um, Ben, another good example is pile driver. You give it gravitational potential energy, and then as it drops, it turns into kinetic energy. But this is the law of conservation of energy. Whatever energy you start with is the energy you finish with, or you'll often hear me say, well, the energy's got to come from somewhere. Where did it come from? Example one. A projectile is launched straight up into the air. If its initial velocity was 75 meters per second, how high does it go? It says use energy and ignore air friction. Okay. Mateo, I know you just joined us, but what's example one asking us to find? How high? And what does it want us to use? We're going to write out the law of conservation of energy. It says the initial kinetic plus the initial potential, or potential initial plus kinetic initial. Initial plus initial equals final plus final. And then before I go any further, I always ask, are any of these zeros? Kinetic energy is the energy of motion. Let's visualize what's going on. Initial, we're starting it on the ground, and we're going up, 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 up. And there's our final. Kinetic energy is the energy of motion. Is there ever a time when we come to a stop? At the top for a split second. So what that means is my final kinetic energy equals 0 for a split second. What about gravitational potential energy? Well, that's 0 when H is 0. Is there ever a time that we're on the ground? Where? What's the I in a brief for? Yeah, I can, PEI, of course, we know that's not a real province, right? Please. PEI, they call themselves a premier. They're a mayor at best, right? So we can go a little further. What was the equation for kinetic energy? It's a half mv initial squared. What was the equation for gravitational potential energy? It's going to be mgh final. There's something else I notice. Neela, is there an m in this term? Is there an m in this term? Is there an m in every single term? Then the m's will cancel out. Because if you divide both sides by m, no m's will be left. What am I trying to find, Matteo? Oh, I think that. Yes? I need to move the g over. What's the g doing to the h? How will I move it over then? Yep. So on my next line, now it's up to you. Some of you, don't write this down, look up, might like to go 0.5 VI squared as you drop it down like a domino. That's fine. You can do that. I like to go drop the VI squared, and I just drop the 1/2 because that's a 2 on the bottom. Why do I do that? Because that lets me tuck Mateo's G down there too. I've got something down there. And then Mateo, if you don't mind, HF, I'm going to write it on the left-hand side. So you can either write 0.5 v squared over g or vi squared over 2g. It's the same thing. Mateo, what was vi? Yep. Don't forget the squared. Divided by 2 times g, 9.8. How high will this go? Good for reaching for your calculators. It's going to go fairly high. Doing some quick math in my head. I think it's in the 200s or 300s. I can't be much more specific than that, though. 287, anybody else? Units, meters. Now, that's if we ignore air friction. Aiden, in real life, there would be air resistance, air friction. And one of the nice things about the law of conservation of energy is it lets me factor that in finally. So B says, suppose we do the experiment, but the projectile only reaches a height of 125 meters. How much energy was lost to air friction? By the way, you can point a little arrow to air friction, and you can put in quotes heat. Air friction or friction is heat. This is still a job for conservation of energy. I'm going to go Ke initial plus Pe initial equals Ke final plus Pe final. But what this question is saying, when it says include air friction or include heat, I'm going to have to add heat. to my final. Are we still starting off on the ground in this question, Mateo? So we can still say that our initial potential energy is 0. How fast will we be going at the tippy top for a split second? So we can still say the final kinetic energy is 0. Carson, what's this want me to find? How much energy was lost to air friction? Yeah, but what did I say that was? What does it want me to find? Heat. How would I get the heat by itself? How would I move this potential energy final over? What's... Yeah. KE initial is going to drop down like a domino, minus PE final. And then instead of writing equals heat, if you don't mind, I'm going to put heat equals, because that way I have it by itself on the left, like we do in math. And now it's time for me to start substituting in my equation. What's the equation, Carson, for kinetic energy, right from your formula sheet? So since it's initial, it'll be a half mv initial squared minus... Okay. Luke, what's the equation for gravitational potential energy, right from your formula sheet? And since it's final, it'll be mgh final. Neela, is there an m in the last term? Is there an m in the middle term? Is there an m sitting right there in heat? Say no. M's don't cancel this time. If you're not sure whether the mass cancels, leave it in and you'll still get the right answer. Anywhere that you would have times by 12, you'll divide by 12. Anywhere you would have times by the mass, you'll divide by the mass. You'll be okay. But I'm trying to show you that stuff does cancel sometimes. Well, let's crunch the numbers here. So Carson, 1.5. I've scrolled down. What was the mass? What was the initial speed at launch? Don't forget the squared. Minus 12 times 9.8. Oh, and they said this time the final height wasn't 287. They said, no, it only went, was it 125? Yeah. We lost some energy to heat. How much? Yeah. Let's see. 0.5 times 12 times 75 squared minus 12 times 9.8 times 125. Did you get 19,050? Nice, works out evenly. Units, heat is energy. Energy is the ability to do work. What are the... Yes. C is nice as well. It says, what's the average force of air friction? Your hint is, I'm going to use my answer from B. Ella, what did we find in part B? Ah, we just found the work done by air friction, which is going to be the force of friction times distance. What's C asking me to find? Get the force of air friction by itself. How would I move the D over? So I get this. The average force of air friction is going to be the work done by friction divided by the distance. What's the work done by friction? That's the heat, 19,050. What's the distance? That's 125. What was the average force of air resistance? So here's yet another way to find a force. This is not F equals ma. This is F equals work divided by distance in this specific situation. What'd you get? 152. Point what? I missed that last digit each time. Sorry, 0.4. Okay, you can write. I'll go to 3 sig figs, and that's a force, so it's newtons. Mr. Dueck has a very cool demonstration. Well, yeah, I do. Sorry, I got to pause the video. Sorry for those of you at home, you missing out. Where do we use the law of conservation of energy, G? So one of the things you may have noticed, I've tried to teach you kind of a trigger here. What do I use here? If there's a collision or an explosion, conservation of momentum. If you see mu or forces, this is a job for a free body diagram. When do I use the law of conservation of energy? We use it when there's a change in height and a change in speed, and especially when there's a yucky curvy path. In other words, we use it to analyze roller coasters, which we'll look at a bunch of, and I'm going to tell you right now, there's going to be a roller coaster on your final quiz because I'm nuts about roller coasters. Ski hills, skate parks, swing sets, anything where there's a change in speed and a change in height and it doesn't follow a nice straight line. Conservation of energy is our best tool to analyze it. So, example 2, I like example 2, skiing. At location Z, a 72 kilogram skier is traveling at 18 meters per second. How high up the next slope can the skier reach if we ignore friction? Okay. Ben, look at the picture. Imagine it continuing forwards. Will there be a change in height? Will there be a change in speed? Is there a yucky curvy path? This is a job for conservation of energy. I always like to label what's initial and what's final. I'm my lazy but organized. So if they give me a picture, I think, Ben, that's initial, and I think final is right there. What's the law of conservation of energy? It says this: initial plus initial equals final plus final. Do I need to go plus heat? Do I need to include heat in this equation? Carson's shaking his head. How do you know? Yeah. Okay. Before we go further, I always like to ask, are any of these zero? Now, potential energy due to gravity is zero when H equals 0. When you're on the ground. Ben, are we on the ground anywhere in this situation? Where, initial or final? So, again, we can cross out PEI. Again, yeah, they're not a real province. Island, how is an island its own province? Vancouver Island, sure, big, lot. Kinetic energy is the energy of motion. Kinetic energy will be 0 when the speed is 0, or the fancy word for your speed is 0 is you're stopped or you come to rest. Is there anywhere that we're going to be stopped? I think at the very top. If we don't use our ski poles, we're going to go up, 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 just like in the skate park. I think we can say that. And so we get what started out as a really complicated situation with hills and curvy paths. We can say, Ben, what's my equation for kinetic energy, right from my formula sheet? That's kinetic energy? Not a half over mv. I think just a half mv squared. Yeah. So it's going to be a half m, and since it's initial, Ben, it'll be vi squared. And what's the equation for potential energy, gravitational potential energy? PE. Yeah. And since it's PE final, it'll be MGH final. Ben, what did you say this question wanted me to find? You know what? It wants me to get this by itself. Now, Ben, is there an M in the term on the right? Is there an M in the term on the left? Is there an M in everything? Masses cancel. We want to find the H. How would I get the H by itself? Mateo, how did we get the H by itself earlier? How did we move the G over? Same equation. And so we're going to get this. The VI squared is going to drop down like a domino. There's going to be a G down there. And then it's up to you. You can put a 0.5 if you like that. I'm happy, Aiden, to put a 2 on the bottom because I still see the 1/2 and I don't have to write the 1. It's the laziest way to write it. And Ben, if you don't mind, I'll put the H equals on the left-hand side. And now we're good to go. Ben, I've scrolled down. What was the initial speed at location Z? Don't forget the squared divided by 2, 9.8. What do you get? How high up the next hill will this skier go? What'd you get, Mateo? Because you're typing on your calculator instead of passively sitting. Ben, what did you get? I'm doing some rough math. I think you're going to get something in the teens, I think. Point, round it off properly. 0.5 or 0.4 or 0.5? What's after the 5? So the 5 stays a 5. Yep. Okay. If you want to go higher, go faster. There's the law of conservation of energy. We're going to finish with example 3. I like example 3. I like example 3. Example 3 is a nice question. Mr. Dueck, you said that last day about a bow and arrow. Yeah, I used to teach archery when I was a summer camp counselor. I love archery, and so there's a good chance you may see this in the future. Let's walk through it step by step. It says, suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. We don't do physics with centimeters. How do I convert centimeters to meters? Sophia's dividing by 100.68, right? Okay. Maddie, what's A wanting me to find? Well, work is force times distance. Did they give me a force? Did they give me a distance? Are the force and distance in the same direction? Yeah, you're pulling backwards and the string's moving backwards relative to you. Okay, we're good. 245 times 0.68. What do you get? 166.6, and that's joules. How much potential energy is stored in the bow? Now, here's where I get a little grumpy. If a student isn't paying attention, they see potential energy and they think, don't write this down. Oh, MGH. That's when you're lifting something. Are we lifting anything in this question? No, but then they'll panic. They'll go, I need an M. They'll look at part C and they'll see a mass right there. G, I don't need H. Well, it's in meters, so I'll use this distance that you pulled it. Is that a height? No, don't do that. I'll gently damage your self-esteem. Instead, your hint is you know the answer. How much potential energy is stored in the bow? 166.6, baby. Because that's how much work you did in pulling it back. It's elastic potential energy stored in the bow. What I'm more interested in is part C. If the arrow has a mass of 42 grams, geez, Dueck. We don't do physics with grams. How do I convert grams to kilograms? Divide by 1,000, and I think if you do that, you get 0.0042 kilograms. Seda, what's C want me to find? Okay. When you let go of the string, here's what really happens. All of your potential energy that was stored turns into kinetic energy of the arrow. That's the law of conservation of energy. That's a little shorter version, but that's what's happening. Yeah. Thank you. Tori gets a candy. Mr. Dueck made it 4.2 grams instead of 0.04, instead of 42 grams. I owe you a candy. Sorry about that. What's my equation? Oh, no, no, not what's my equation for potential energy, not mgh. I know how much potential energy I stored, force times distance. How much did I store exactly as a number? 166. So here it's going to be 166.6. Ben, what's the equation for kinetic energy? Say it. What did you say they're asking me to find? Get the V by itself. How will I move the 0.5 over? How will I move the M over? So if you don't mind, I'm going to do it right on this line here, 0.5 M. That gives me a V squared. A V what? A V squared. Talk to me. Yes. Cross out the squared. Square root. I'm going to get V equals the square root of 166.6 divided by 0.5 times 0.042. Type that into your calculator, see what you get. Say it, what'd you get? No, it's going to go faster than that. I didn't do this in my head, but I'm sure I would have made this up so that it's in the 70s, 80s, 90s, or 100, because that's roughly how fast bows travel. 89 point, okay? So make sure you put the bottom in brackets and right, all that stuff, right? Should be 89.1 meters per second, which is about right. I've seen people fire bows. They go fast, but not like a bullet that you can't even see it. You can follow it as a blur. 89 meters per second, that's the length of the football field in 1 second. Yeah, your eyes could follow that. Like it's a blur, but it's not like it's so fast you don't even see it coming. That's about right. Bows tend to go around 100 meters per second, depending on how fast or how much you pull, how strong. Okay. So ballpark, that seems to be good to me. And I like that question. I like archery. My Nerf dart gun works very, very similarly. We're going to pause here. Pause the video, but I'll show you my Nerf dart gun.